Hello. Iron Maiden made a song. So I'm wearing the Iron Maiden T-shirt, by the way. They made a song entitled 666. Sorry, the number of the beast. Okay, which alludes to the number 666, which has a negative connotation to most of the people because it represents evil and stuff, and that's why it's heavily present in the heavy metal community because of its evilness and stuff. And if you came to watch this video to expecting that we're gonna explain its evilness, I'm sorry to disappoint you that this is a clickbait title, okay? Because in fact, what we're gonna do is even more fascinating than that, okay? We're gonna be looking at a problem which involves the number 666, okay? So of course, it's still the number of the beast, so-called. It's still there, but it is hidden in the following sum, okay? So the sum that we're gonna tackle is 6 plus 66 plus 666, the number of the beast, okay? But plus 6666 all the way up to 666, whatever how many sixes you want to add, okay? So in this, the last term, there are n sixes there, okay? And I want to look at the number 6 because yeah, people think it's like a bad number and so on, which is sad, because 6 is like the smallest perfect number, and all that stuff. So let's do this problem that involves nothing but sixes, and let's have some fun. Okay, how do you add this? Okay, so the first impulse when you want to add this is you get like a calculator or a computer and then you input everything else, okay? But however, when let's say n is like 100 or 1000 or 1 million, that's gonna be cumbersome, okay? So we want to find an elegant way, to close the sum so that given any n, we can like tackle that sum in the first place, okay? And since this number 666 in particular is very prevalent in metal, let's use the metal symbol, the heavy metal symbol, to represent the sum of 6 plus 66 all the way up to n sixes. And to indicate that there are n sixes, let's put the subscript n, okay? So for example, the heavy metal of 1 is 6. Okay, the heavy metal of 1, because you're just adding a single term, which is 6. What is the heavy metal of 2? Well, you're just adding two terms, which is 6 plus 66. Well, that's nothing but 72. Okay, but what is the metal of n in general? Okay, so one way to tackle this is typically when you're dealing with a series that contains like n terms, you always want to find a way so that you can compress the term, the sum in terms of the original sum itself. Okay, so in other words, on the right hand side, we want to extract something that looks like the metal sum. Okay, and here's one way to do that. So let's write 6. But then 66, let's write it as 60 plus 6. Okay? 666, let's write it as 660 plus 6. 6,666, let's write that as 6,660 plus 6. Okay? And so on all the way up to 6666666, blah, blah, blah. This time there are only n minus 1 sixes. Why? Because the last unit digit is 0 because you separated the 6. Okay? Now, if you combine all the sixes, the single 6, how many are there? So you have 1, 2, 3, 4, blah, 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 all the way up to the last one, which is the nth single 6. Okay? So in other words, there are n of sixes that you've separated. After separating that, what do you have left? Well, you have 60 plus 660 plus 6,660 plus blah, 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 all the way up to 66666 with a 0 at the end. And then this time there are only n minus 1 sixes. Okay? What do we do next? So this is what I mean. In order to make it look like the original metal sum, let's factor out 10. Okay? So you have 6n. All these guys here, we can factor out 10 because they have 0 at their digits place. So you have 10 factored out. So you have 6 plus 66 plus 666 plus all the way up to 6, 6, 6, blah, 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 6. There's no more 0 because you factor out 10. But this time, there are only n minus 1 sixes. Okay? So now, do you agree that the whole thing in the parenthesis is nothing but the metal sum of n minus 1? In other words, the one in the parenthesis, you're adding 6 plus 66 plus 666 all the way up to n minus 1 sixes. Okay? So this is what I mean. Try to, make the sum on the right-hand side similar to the whole sum on the left-hand side, okay? So you have metal n minus 1. And you can even do a further move, because what you can do is you have 6n plus 10, but would you agree that the metal sum of n minus 1 is nothing but the metal sum of n? How do you make the metal sum of n become the metal sum of n minus 1? Well, you subtract from it n sixes, correct? So you have minus 66666 n instances of this sixes right here. So now we were now able to write the many terms on the right-hand sum as the right-hand side as the in terms of the original metal sum. Okay, so now this is just a simple algebraic simplification. So you have metal sum of n, you have 6n plus 10 metal sum of n minus, so I distribute that 10 here, so you have 6, 6, 6, blah, 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 up to 6. There are n sixes here still, but since you multiply it by 10, there's a 0 at the end. Okay, so let's simplify. So you have 10n on the right-hand side. You have metal n on the left-hand side. So 10 metal n minus metal n is 9 metal n. Let's put that on the left. So 9 metal n equals, so that's now on the left. So the 666 guys, the n sixes with a 0 becomes positive. 6, 6, 6 all the way up to 6. There are n sixes minus 6n. Is that right? So 10, 9 minus plus, yeah, that's correct. Okay, and of course we can factor out here the 6. This becomes 6 multiplied by 1, 1, 1, 1. So now there are n instances of 1s. There's a 0 at the end, minus n. Okay? And of course, to solve for the metal sum of n, you just divide the right-hand side by 9. Doing so gives you 6 over 9. You simplify that fraction, that gives you 2 over 3. Okay? That's right. And then 1, 1, 1, 1, 0, minus n. There are n ones right here. Okay? So you can stop here. You can say, oh, I've simplified it better. Yeah, but it's still nasty because there are n ones. Like, that's annoying to deal with. Okay, you know? So let's try to extract that out, that n ones. Okay? N pieces of ones, but with a 0 at the end. Note that you can write this, okay? So look at this carefully. I can write this as 1, 1, 1, blah, 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 0, 0. So now there are n minus 1 ones plus 10. Okay, I separated 10. And then you can separate, so you have 0, 0, 0. Now you have n minus 2 ones plus 10 plus 100, and so on. Okay, so in fact, you can write this as 10 plus 100. So you keep extracting powers of 10 from it, plus 1,000 plus 10,000, all the way up to, so how many zeros will the last one be? So since you began with n ones, excluding the 0, you've extracted n minus 1 ones in all. Okay, so in other words, the last guy right here will have n minus 1 zeros, but you still have a 0 on the last unit term. Okay, in the left hand side most place. Okay, so in other words, if you write this using scientific notation, this is just 10 plus 10 squared plus 10 cubed plus 10 to the fourth plus blah 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 up to, so you have n minus 1 zeros. If you include the last one, that's like 10 to the n. Okay? What is this sum? This sum is nothing but not arithmetic, geometric sum. Okay, so to get this sum, you get the first number 10. To get the subsequent terms, you keep on multiplying it by the same number, in this case 10. So you have 10 times 10, so plus 100. 100 times 10 plus 1000. 1000 times 10 plus 10,000, and so on. You keep on multiplying the succeeding terms by 10. Okay, so in general, a geometric sum looks like the base number, so any number, and then the next term, you just multiply it by a constant. We give this a symbol r because it's the ratio. If you divide a term with its previous, the term before it, you get a constant which is r. Okay, and then the next term, you multiply it by r again, so you have ar squared, and then the fourth term is ar cubed, and so on, all the way up to, of course, the nth term will be ar to the n minus 1. Why not to the n? Because you're adding n terms. Note that you still have an a in the very first term. Okay, so you only reach up to a to the a times r to the n minus 1. Okay, so in our case above, a, the base number, is just 10. R, the constant ratio, is also 10. So it's even simpler in our case. How do you add this? How do you add a geometric sum? Okay, I forgot. But we can like derive it. Okay, so typically what you do is multiply this by 1 minus r, r minus 1, because in our case the ratio is greater than 1. Okay, so typically there are geometric sums where the ratio is less than 1, so you multiply it by 1 minus r if you want to get the sum. But here we multiply it by r minus 1, so this gives you r minus 1 multiplied by a plus ar squared, blah blah blah, all the way up to ar to the n minus 1. Let's simplify. So r multiplied by the geometric series gives you ar plus ar squared plus ar cubed plus blah blah blah, all the way up to ar to the n, because the last term is ar to the n minus 1 multiplied it by r. Okay, minus, so the geometric sum just multiplied by 1, so you just copy it. So a plus ar cubed plus blah blah blah, all the way up to ar to the n minus 1. Okay, and since you're subtracting, note that this ar will cancel this ar, this should be ar squared. Okay, so you have ar squared, ar cubed, and so on. This ar squared will cancel this ar squared, this ar cubed will be cancelled by the ar cubed here, and so on. Okay, everything here will be cancelled up to ar to the n minus 1. ar to the n, nothing will cancel that, and a is not canceling anything. Okay, so the remaining term here will be ar to the n minus a. Okay, so therefore this you can write as a to the r minus 1, and then gn therefore is equal to a to the r over to the n minus 1 divided by r minus 1. Okay, in our case above, for the 1, 1, 1 with n number of ones, our a, the base number, is 10, and our ratio is also 10. Okay, therefore 1, 1, blah 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 blah, 1, 0, and ones, the sum of that, which is 10 plus 100 plus 1000 plus 10,000 and so on, is just equal to a, which is 10, multiplied by r to the n, so that's 10 to the n minus 1, over r minus 1, so that's just 9. Okay, and this guy right here is the one that we're gonna use in our original metal sum. Okay, that's what we needed it for in the first place. So let's rewrite the metal sum here. The metal sum is now equal to 2 over 3 multiplied by the 1, 1, 1, 1, which we know is now 10 times 10 to the n minus 1 over 9 minus n. Okay, so we can factor out 9. So this will give you 2 over 27. We can distribute 10. So you have 10 to the n plus 1 minus 10 minus n. Minus, since you factored out 9 and n doesn't have a coefficient, so it has to have 9n over there because you factored out 1 over 9. Okay, so that's what happens. So we claim that this gives us the metal sum. Let's try. The metal of 1. What's the metal of 1? Of course, that's just 6. Okay, we said that a while ago here, right here. Okay, in our example, the metal of 1 is just adding the 6 with a single 6 in it, so it's just 6. So let's hope that this gives us 6. If not, then we're screwed. Okay, so we have 2 over 27. 10 to the n is 1, so 10 squared, which is 100, minus 10 minus 9. So what is that? That is 2 over, so 27, let me write that as 2 times 9. Because 100 minus 10 is 90, minus 9 is 81. 81 is 9 times 9. Okay, so you have here, this will give you, oh, I'm an idiot. Wait, 27 is not 2 times 9. 27 is 2 times 3. Okay, 27, oh, 2 times 3. I meant 3 times 9. Okay, that's 27. Okay, and I wrote it that way because 81 is exactly divisible by 9, so you have that. And then 2 times 9 is 18 divided by 3 is of course 6. Okay, so it works out well. I leave it to you to verify the metal of 2. It should work. Okay, so now we have a very beautiful metal sum of n. You add 6 up to n number of them, you have this metal sum. Let's not stop there because it looks awesome. I'm thinking, what if we change 6, which we picked out earlier because it's related to the number of the beast, but what if 6 is not like your favorite number? What if we pick up 1, we pick up 2, we pick up 3, whatever, okay? So let's call that sum, I don't know, R for repeated, okay? So the repeated sum of dn, so this means you take any digit d, and then you repeat that digit again, you repeat it again, all the way up to until you get to the point where there are n of them, okay? Of course, in our notation, R of 6n, this was our metal sum, okay? So our metal sum is just a special case of our repeated sum here for the case where the digit is equal to 6, but we can pick anything else between 1 to 9, okay? Don't pick 0, 0 will be trivial, okay? So we pick anything between 1 to 9, you have R sub dn, okay? How do we do this? We use the same technique that we used a while ago, okay? We factor out, we separate out d from all the rest, so this will give you d0 plus d0 plus d. So when I say d0, when d is 1, that means 110. When I say d0 and d is equal to 2, that means 220, and so on, okay? All the way up to, so d blah blah blah, d0, n minus 1, or d. So here, n number of d's, okay, plus d, okay? So it looks very similar. So now what happens is, we know that there will be n number of d's here, okay? And then what we're gonna do is we're gonna factor out 10 from the remaining d plus d plus blah 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 all the way up to d. This time there are only n minus 1 d's here, okay? And the one in the parenthesis is of course 10 multiplied by the repeated sum of this time d minus 1. Sorry, I'm an idiot again. The repeated sum of the digit d, but there are n minus 1 of them, okay? And again, like what we did before, the n minus 1 repeated sum, n minus 1 of them, can be written as n numbers of repeated sum if you just subtract from it the last term, which contains n number of these. Okay? And again, the simplification is similar from a while ago. So you have RDN equals DN. Let's distribute the 10. So you have 10R sub DN minus DD blah blah blah, blah up to D. There are N D's here. There's now a 0 at the end because you multiply it by 10. Let's simplify algebraically. You have 9R D sub N is equal to D 0 n instances of D's minus Dn. Okay, again we can factor out the D. It will give us 1 1 1 1 0. Here there are n number of ones minus n. This term is just similar to the term here, okay? Because we've already factored out the D dependence, okay? So in other words, if you simplify it again, so you have R D sub n, this will be equal to D over 9. The 1 1 1 1 1 1 n ones with a 0 at the end, we've already established that that is equal to 10 to the n minus 1 over 9, and then you have minus n. And again, if I factor out 9, this gives me D over 81. I distribute 10 to the n plus 1 minus 10 minus n. Bam! So we have a generalized repeated sum for any digits D, including 6. Okay? Let's look at the most trivial example. What's the most trivial example? Of course, the most trivial example is R sub 1 1. What does that mean? We pick the digit 1 and then there's only one of it. So it should be 1. Okay? So let's see. This is equal to D is 1 over 81 multiplied by 10 squared minus 10 minus only 1 of it. Okay, so you have 100 minus, wait, I'm missing something. You have, I missed the 9 here when I factored out 9. Okay, so note that you factored out 9 from here, so you have to have 9 there. Okay, so this should be minus 9. Okay, so you have 100 minus 10 is 90 minus 9 is of course 81. So this gives you 81 over 81, which of course is 1. Okay, very trivial. And in fact, if you notice, the what do you call this? The one in the square brackets, it is independent of D. Okay, so in other words, we can do something like, I don't know, let's make it n equals 2. Okay, so that means you're adding 1 plus 11. Okay, so R of the digit is 1 and then n is 2. So from our notation, this means 1 plus 1 1. This is 12. Okay, so this is equal to, let's see if is it equal to 12 if we use our formula. So you have 1, which is D, over 81, and then 10 to the, this time n is 2, so that is 1000 minus 10 minus 9 times 2, because n is 2, 18. Okay, of course this gives you let's not write it there, let's write it here. This gives you 1 over 81. 1000 minus 28. 1000 minus 28 is 972. Okay, and again, to divide that properly, let's write 972 as 9 times 100 plus 9 times 8. Okay, over 9 times 9. So this will cancel. You have 108 divided by 9. What is 108 divided by 9? So 108 divided by 9, it's 12, right? Because 9 times 10 is 90 plus 18 is 108. Yeah, so it is 12. So our equation checks out, okay? So in this case, we picked the digit 1, and we obtained what do you call this? The number n equals 2. So we obtained the repeated sum, which is equal to 12, okay? And in fact, the amazing thing is d equals 1, okay? Note that if you, let's not make d equals 1. Let's make it some arbitrary d, but let's pick n equals 2 still, okay? So I'm doing that because, you know, d is independent of the number that we've already solved here. Sorry, that should be 81. 1 over 81, 10 to the 3 minus 10 minus 18. We've established that this whole thing right here is 12, right? So in other words, RD2, okay, you pick any digit, you pick the digit plus repeat it, that sum should be equal to 12 times D. But that's amazing. What does that mean? Okay, so it means n equals 2. Okay, so here's what it means. For when D is equal to 1, okay, that implies 12 times 1, which is of course 12. This is just equal to 1 plus 11. Why? Because we pick D to be the digit 1, and our n here is equal to 2. Okay? How about when D is equal to 2? That means 12 times 2, which is 24. Aha, that's just 2 plus 22. Okay? So that's an amazing way to, you know, remember 12 multiplied by any digit, right? Because this is 12D. D is between 1 to 9. So someone asks you, what is 12 times 9? Oh, 12 times 9. Or what is 12 times 8? 12 times 8. That's easy because I know that when D is equal to 8, okay, that is just 12 times 8. If you find that hard, note that that is just equivalent to adding 8 to two numbers of two instances of 8. So that's 8 plus 88, which is 96. Is that correct? 12 times 8 is 6 carry 1. Yeah, it's 96. Okay, very awesome property. So you have like D equals 9. What does that mean? 12 times 9 is nothing but 9 plus 99, which is of course 108, which of course we've seen here. Okay, 108 over 9, which we said was 12. But amazing, right? So you have 12 times, 12 has this property that if you multiply 12 by any single digit number, the shortcut is you take that single digit number, you add it with, you just repeat that single digit. So what's 3 times 12? 3 times 12 is just 3 plus 33, which is 36. What is 12 times 4? 12 times 4 is just 4 plus 44, which is 48. What is 12 times 5? 12 times 5 is just 5 plus 55, which is 60, and so on. Okay, very, very interesting. Now, what if I make, now I'm interested of making RD3, okay, because you can always factor out D, and then you can always solve for this coefficient right here. So when D is equal to, when N is equal to 3, you have 1 over 81, 10 to the 4th, minus 10, minus, you have 9n. So 9 times 3 is, 9 times 3 is 27. Okay, so you have that. So I'm gonna need my calculator here now so that we won't mess up with our, you know, basic arithmetic, right? So let's do 10 to the 4th is of course 10,000 minus 10 minus 27 equals 9963. So this is equal to D times 9963 divided by 81 divided by 81. This is, Wait a minute, that's awesome. So RD3 is 1, 2, 3 times D. Let me write how awesome that is. RD1 is 1 times D. Correct? Because when n is equal to 1, you're just speaking, the sum is just the digit itself. So 1 times D. RD2 is 2 times, no, sorry, not 2 times D. It's 1, 2 times D, which was the 12 a while ago. RD3 is just 1, 2, 3 times D. So let's see if the pattern is correct. Is RD4, is it equal to 1, 2, 3, 4 D? So what is this? This is just D times 1 over 81. When n is equal to 4, you have 10 to the 5th minus 10 minus 9 times 4 is 36. So let's go to our trusty calculator. 10 to the 5th is 100,000 minus 10 minus 36. 9954 divided by 81. Man! What? This is awesome. So when n is equal to any digit, the repeated sum of that digit up to the nth term is just 1, 2, 3 up to that D times D. Let's investigate why does that happen. Why does that's very cool. So let's write it down. Let's look at the instance of RD3 equals 1, 2, 3 times D. And in order so that we can investigate it properly, let's simplify. Let D be the digit 1. So note that originally we've picked the digit 6, but let's just pick the digit 1 for simplicity's sake. Okay? So that means R1 of 3, you add 1, you repeat it up to 3 repetitions. So that means 1 plus 1, 1 plus 1, 1, 1. So this is 1 plus 1, 1 plus 1, 1, 1. This is just 123, which makes sense. But why does it do that? It does that because 123 is, of course, 100 plus 20 plus 3. I know why. Okay, so in general, okay, I know why. So in the general, when you have RD3 equals 1, 2, 3 times D, that's just equal to D multiplied by 100 plus 20, which is 2 times 10 plus 3. Okay, so that means this is equal to when n is equal to 3, you have let me see if I got this correctly. 100 plus 20 plus 3. Okay, so why does it work? It works because you have Okay, so I think I can write this in general as let me think. This is 1, 2, 3 times D, 1 times 20 times D. Okay, it's a very interesting pattern that we got here, and what I want to do is I want to like understand why it happens that way. Okay, so 100 plus 20 plus 3, this is our 123 right here. Okay, so D times 100. Of course, this is equivalent to adding D plus D, D plus D, D, D. I know. Okay, I get it now. So it's because, it works because you are multiplying, yeah, I think I know why it works. You're multiplying D in the units digit 3 times. So you have D, 1, 2, 3. Okay? Now in the tens digit, you're multiplying it twice. So you have 1, 2, and then 1 time in the ones digit. Sorry, in the hundreds digit. So you have the D there. Okay, so that's why it works. That's why it works in general. Okay, so in fact, in general, we can write it as, let's go back now to our RDN. Okay, so in general, we can write this as our original equation was, let me go back to that. D over 81 multiplied by 10 n plus 1 minus 10 minus 9n. However, from the pattern that we just saw, this means that in general it is of the form. So let's put a question mark because we're not sure. It is of the form D multiplied by 10 to the n minus 1 plus n minus 1 multiplied by, let me think, my eraser is weird. Let me change it to the stroke eraser. Okay, d10 to the n minus 1. I'm trying to recreate the pattern here above, up to n minus 1 up to n. N minus 1 n plus blah blah blah. Shucks, I'm in eraser mode, sorry. Plus blah blah blah. Is it n minus 1 n up to n? Our last term is n because n is equal to 3. The next one right here is n minus 1 10 to the 1. Okay, this corresponds to this term. And then if we continue the pattern, we have 10 squared n minus 2. I think that's, yeah, I think that's the one. Is that right? Yeah, I think that's the general pattern. So you have from n plus n minus 1. So to make it even more explicit, this n has a factor actually of 10 to the 0. Okay, this is the 3 right here a while ago, because for that example n is equal to 3, plus n minus 1 10 to the 1. So that's the one here, 2 times 10, plus n minus 2 10 to the 2, blah blah blah, all the way up to, so eventually you reach n minus n 10 to the n. But of course n minus n is equal to 0, so you only reach up to 10 to the n minus 1. Okay, so that's the general pattern. But my question is, of course, everything is multiplied by d. Okay, so in other words, what I'm thinking is, for example, when n is equal to 5, I can write nd5 as 1, 2, 3, 4, 5 times d, when n is equal to I think we have an issue now. When n is equal to 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, D. Okay? What this means is when you let D equals 1, the repeated sum of the digit 1, when there are 9 of them, is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you see the issue? The issue that I'm seeing is, does it continue the pattern when n is equal to 10? Because obviously here, eventually you run out of digit for your n. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. When you reach n equals 10, is it still given by 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, D? Okay, that's the question. And I don't think that's the case. For example, R1 10, is it equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Is it equal to that? I don't think so. I think the pattern will change because there is now the complication of carrying it. Okay, let's try that. So what is R1 of 10 again? So you're adding 1 plus 11 plus 1, 1, 1 all the way up to 10 repetitions of 1. So let's do it in the calculator. 1 plus 1, 2 plus 1, 2, 3 plus 1, 2, 3, 4 plus 1, 2, 3, 4, 5 plus 1, 2, 3, 4, 5, 6 plus 1, 2, 3, 4, 5, 6, 7 plus 1, 2, 3, 4, 5, 6, 7, 8 plus, so note we're reaching the 9 here, so it should be D is equal to 1, so it should be 1, 2, 3, 4, 5, 6, 7, 8, 9. So plus 1, 2, 3, 4, 5, 6, 7, 8, 9 instances of 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. So according to our conjecture, if we reach 10, it should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0. And I don't think it will work because it will now carry, so I don't think it will work. I think if it carries, there will now be like a 0. Yeah, it will be, I think it will be followed like by 2 zeros or something. So 9, this is for 9 ones plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, it's not anymore 1, 0. Okay, so if we continue, let's add 11 instances of 1s plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11, okay. Yeah, but it looks... yeah, I think it will go 1, 2, 3, 4, 5, 6, 7, 8. Did you notice the 8 is gone? Yeah, because the carry will cancel it, yeah. And then plus 12 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. So, yeah, is it? 1, 2, 3, 4, 5. Yeah. Okay. So it doesn't hold. So, but anyway, yeah. But at least we found a very nice. So in general, we learned that the repeated sum of any digit D repeated it n times. This is always correct. The D over 81. 10 to the n plus 1 minus 10 minus 9n, and then we enter the rabbit hole of, since D is outside the parenthesis, the term in the parenthesis is dependent only on n, we tried playing the values for several n, and we found that for n, between, if n belongs to 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9, you can write your sum of RDN as something like 1, 2, 3 up to n times D. Okay, so in example, RD of 7 could be written as 1, 2, 3, 4, 5, 6, 7 multiplied by D. Okay, so yeah, so I think that's a very good result so far. So I think this is a good stopping point for us, So we started with the number of the beast, 666, and then look where it got us. Okay, so yeah, very very amazing pattern. So here's what I would like you to investigate, because we're investigating single digit number. So if you want to have like a takeaway, an assignment or something that you can make do on your own, what if we consider repeated sums of two-digit numbers? Okay, because we're doing here the simplest case, just one digit. Okay, so for example, what that means is take, let's say, 13. Okay, so so for the case of let's call it, I don't know, d sub 2 or something, because there are now two digits. Okay, or no, that's confusing, but let's just call it 13. So you know what I mean when we say 13, we want to find the sum of 13. So let's draw a box there. That's like the variable of n. That means you go 13 plus 13 13 plus 13 13 13 plus all the way up to n instances of 13. Okay, so the question is, for any two-digit numbers, that's a lot. That's like starting from 11. So those cases with the same digits, I think they are much simpler, because you can use our results here, because like 11, you repeat it, it's just like 1 1 1 1. Okay, except the times you repeated them, odd number of times. But for like not the same like 13 or let's say 19, so 19 plus 1919 plus 191919, what is the general pattern? Okay, but I'm not gonna do that, because we're like we've been doing this for a lot of time already, so I think this is enough. So I hope you learned something in this number of the beast excursion. Okay, and I'll see you guys next time. Thanks for watching, and bye bye.